In this segment, we're going to talk about KBOs and comets. Let's first talk about KBOs. A Kuiper Belt object is an object in the Kuiper Belt, which is a region just beyond Neptune's orbit, and it contains icy planetesimals that are remaining from the formation of the solar system. So a Kuiper Belt object is an icy object that is orbiting in the outer fringes of the solar system beyond Neptune's orbit and almost in the plane of the solar system. In this cartoon image from your textbook, we see the solar system. If you can look carefully, you see that this one is Jupiter. I'll label it J. This one is Saturn. And this one is Uranus. And this one over here is Neptune. And they're showing you a path of a comet going around the sun, and it's coming from outside this region that is outside the orbit of Neptune. So it's out here, and that is where your Kuiper Belt objects are located. So if you look closely, you'll see these little brown dots in the image, and those are your Kuiper Belt objects. And notice they are all nearly in the plane of the solar system. Now remember that the distance between the sun, let's put the sun over here, and the Earth is 1 astronomical unit. Now the Kuiper Belt extends outward to basically about 50 astronomical units. Some are further out than 50, but 50 is about where most of them are contained. So you can see the Kuiper Belt extends 50 times beyond the orbit of the sun, of the orbit of the Earth around the sun. On the bottom right is an image of such a Kuiper Belt object. There it is. So it's like one of these little Kuiper Belt objects. This one is KBO 2000 FV53. It was discovered in the year 2000. It is about 120 kilometers in diameter, and it moves against the background stars. So you can see this is a background star. And you can see its movement from there to here. Kuiper Belt objects are small bodies with dark surfaces that make them very hard to detect from Earth. We were able to discover this Kuiper Belt object because of its movement relative to the background stars. The background stars didn't move. It was the Kuiper Belt object that moved, which thus allowed us to discover it. Now, how does a Kuiper Belt object become a comet? So if a Kuiper Belt object gets disturbed or agitated from its Kuiper Belt, and it travels in to the inner solar system, like they're showing you here, and it swings around the sun, then it has the chance of becoming a comet. So let's go look at comets. A comet is one of the small icy bodies that orbit the sun. It produces tails of gas and dust when it nears the sun. So when an icy body planetesimal lives out in the Kuiper Belt, it is this small, icy, dark object. But if it gets agitated and pushed into the inner solar system, it comes in and then it starts to develop these tails. And as it swings around on its orbit into and around the sun and then back out into the Kuiper Belt. So here's an image of a comet on its orbit around the sun. And you can see the two tails. This one is the gas tail, and this one is the dust tail. So you see the two tails that are formed when the comet orbits near the sun. Now let's look at a comet's orbit. Now comets can orbit in the same direction as the planets orbit around the sun, or they can orbit in the opposite direction. So comets don't really have a set preferential direction of orbit around the sun. In this particular case, in this snapshot, it's actually 19 snapshots composite together to give us this nice beautiful image, and we are looking at Comet Holmes in its orbit around the sun. And if you look at the dates, here it is in its orbit where it started, and if you just follow the path, you can trace out the orbit of the comet. So you can see that the comet gets brighter in this region. So we know that the comet that has to be orbiting the sun, so the sun has to be right about here, because we know that the tails and the coma start to form when it's approaching or nearing around the orbit of the sun. Let's look at these comet parts. Let's look at this image of Comet Mercator and find its comet parts. First part we want to find is the coma. The coma is located right there. That part's the coma. Then we notice we have two tails. We have got this straight tail called the gas tail, or sometimes called the ion tail. And we see this flat, wide tail, which is called your dust tail. Now inside the coma is the nucleus. Let's look at these parts individually. The coma is the glowing head of a comet, and that would be this portion of the comet. That's your coma. Now let's look at the dust tail. The dust tail is a tail of a comet formed of dust. It is blown outward by the pressure of sunlight. So there is your dust tail. Notice that it's being blown outward and is by the pressure of sunlight. So we know that the sun has to be over here somewhere, because the sun is sending out charged particles and it's sending out light, and it is the sunlight that has pressure that is pushing on the dust of this comet, and it pushes it away. Now if you look carefully, you'll see that the dust tail is like this curved region. So it's got this curvature to it, as opposed to the other tail, which is your gas tail or ion tail, which is really straight. Let's go to the ion tail. The gas tail, otherwise known as the ion tail, is the tail of a comet produced by gas blown outward by the solar wind. So this gas they're talking about here is the gas that's coming from the comet. So it's produced in the comet and is being pushed outward in this straight tail. Now we know the sun is located over here, and the sun puts out this solar wind. And the solar wind has ions, and as soon as those ions hit the comet, it pushes the gas in the tail straight away from the sun. So you can draw a line from the sun through the comet and trace along that ion or gas tail. Now the last part is called the nucleus. Now the nucleus you can't see. The nucleus is in the center of the coma, or near center of the coma. The nucleus is the solid core structure of a comet. In the bottom right is an image of the nucleus of a comet. As you can see, it is grayish or shades of gray, and not spherical. It is potato-shaped or very oblong or of strange structure shape. It is the gas and dust released by the comet's icy nucleus that produces a head, or the coma, of the comet, and that gas and dust is then blown outward away from the comet, and it is pushed outward to create the dust tail by the sun's pressure, and then the solar radiation pressure, and the gas tail is pushed outward by the solar wind. Now let's take another look at that comet's orbit. Now in this cartoon drawing from your textbook, the comet is coming in and orbiting in the counterclockwise direction. So the Kuiper belt is somewhere out there. As the comet nears the sun, it starts to form these coma and tails. So if you look closely, you can see the coma that are formed. And you can also see this white tail that's pushing out, and that white tail is going to be your gas tail. Now if you look very closely, you'll see another tail, and that tail is your dust tail. Now compared to the gas tail versus the dust tail is much longer than the dust tail. Also notice the sun's location. So here's your sun in the center, and if you draw lines from the sun to the comet, you'll see that it goes through the, oops. Now what happens to all that dust that's left behind as the comet orbits the sun? Well, that dust that gets left behind traces out the orbit of the comet, as shown. So in this particular diagram from your textbook, we're not going to focus on the tails or the coma. We're just going to be focusing on the orbit, which they've already indicated is in the counterclockwise direction around the sun. We know the Kuiper belt is out here. And we know as the comet either comes in or comes out, or approaches in or is going away from the sun, that the comet coma and tails may form. And if they form, you'll see that the dust will be left behind and it will trace out the orbit of the comet. So if you look in the upper right, I have put an image from our textbook. It is an infrared image of the comet Encke, and what we see is millimeter-sized rock particles that are left behind as the comet orbits around the sun. And those left behind rock particles glow as they are warmed by the sunlight. So there's the orbit of the comet, and so it might come from an area, region just like that. Now let's look at short period comets. We've been talking mostly about short period comets. Short period comets are comets that are nearly always from the Kuiper belt objects. Their orbital periods of the comets are usually less than a couple hundred years. So the comets you may have heard about, like Hale-Bopp or Halley's Comet, these are short period comets. Now what about long period comets? Long period comets are comets that are nearly always from the Oort cloud. The periods of long period comets are usually more than several hundred. We're talking more than 200 years. Now what do we mean by this Oort cloud? The Oort cloud is a cloud of icy bodies that acts as the primary source to most of the comets that we see. The Oort cloud extends from the outer part of the solar system to roughly 100,000 AU from the sun. So in this cartoon image, we see that the solar system is the tiny dot in the center. So all of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and the Kuiper belt is all contained within that tiny dot. And surrounding it, you'll see these blue dots in this spherical region. That is your Oort cloud. Now, how can an Oort cloud act to be the source of most of the comets that we see? Well, let's look at Comet Halley as an example, which is a short period comet. Comet Halley appears to have began as a long period comet from the Oort cloud. From a close encounter with Jupiter, the orbit of the comet became altered and it went from a long period comet to a short period comet. So as you can see, unlike the Kuiper belt objects, which pretty much orbit in the plane of the solar system, the Oort cloud comets orbit in all directions. They can come from any part of the cloud, and they can go in the same direction as the planet's orbit, or they can go in the opposite direction. There's no sense of motion or direction of comets from the Oort cloud.